Welcome to L'Hopital's rule. So we're now going to look at essentially curve sketching and limits mixed together. So far in curve sketching, we've looked at finding local extrema, right? We've looked at increasing, decreasing. We've looked at relative extrema. We've looked at concavity. We've looked at points of inflection. The things that we really haven't looked at yet are those that have to do with limits. So we haven't particularly looked at discontinuities. So we haven't spent much time on discontinuities. Vertical asymptotes. Or end behavior. And end behavior, I refer to essentially what the function is doing as x goes to plus or minus infinity. So all of these involve limits. So discontinuities, vertical asymptotes, and behavior all involve limits. And sometimes these limits are not as easy to find. So if these limits so sometimes these limits are a little more complicated than we would like. And L'Hopital's rule is going to deal with a couple very special cases. So recall, if we have a limit as x goes to c or infinity, right? Of f of x over g of x. If this goes to infinity over infinity or 0 over 0, it is what is called indeterminate. And what that means is that it could be finite or it could be infinite. And it could be any finite number. So L'Hopital's rule will give us a shortcut for this particular case. So L'Hopital's rule gives us a shortcut for evaluating these limits. And so what that shortcut is if the limit as x goes to c of f of x over g of x goes to either infinity over infinity or 0 over 0, then the limit as x goes to c of f of x over g of x is actually exactly the same thing as the limit as x goes to c of f prime of x over g prime of x. So instead of having to do algebraic manipulation, we can actually just take the derivative of both the numerator and the denominator and then evaluate the limit from there. So for example, let's consider the limit as x goes to 0 of sine of x over x. So this was one of our special limits from earlier in the course. Sine of x goes to 0, x goes to 0, so this is a 0 over 0 case. Since we have 0 over 0, that means that we can apply L'Hopital's rule. So what we have then is that the limit as x goes to 0 of sine of x over x is equal to the limit as x goes to 0 of the derivative of sine of x over the derivative of x. And of course, this gives us the limit as x goes to 0 of the derivative of sine is just cosine of x. And the derivative of x is just 1. Taking this derivative, then we wind up, taking this limit, we wind up just getting cosine of 0, which is 1. So this was what the special limit evaluated to. The limit as x went to 0 of sine of x over x is 1. This is another way for seeing where that limit comes from. For another example, let's go ahead and evaluate the limit as x goes to 0 of cosine of x minus 1 over x. So again, this will go to 1 minus 1 over 0, otherwise known as 0 over 0. Since we have a 0 over 0 situation, this means that L'Hopital's rule applies. So we can go ahead and take this limit. So we have the limit as x goes to 0 of cosine of x minus 1 over x is equal to the limit as x goes to 0 of the derivative of cosine of x minus 1 over the derivative of x. From here, I'm just going to make sure I wrote the fraction in the previous. I did. Okay. So I apologize for the scrolling there. From here, we take our derivative. So we are looking at the limit as x goes to 0 of derivative of cosine x is sine of x. That minus 1 goes to 0. The derivative of x is just 1. Evaluating this limit, we can go ahead and plug in. We are just looking at sine of 0, otherwise known as 0. And the limit as x goes to 0 of cosine of x minus 1 over x is in fact equal to 0. Let's go ahead and do one more. Let's evaluate the limit as x goes to 0 of e to the x minus 1 over x. So again, this winds up being 1 minus 1 over 0, or we have a 0 over 0. 0 over 0 tells us that we can use L'Hopital's rule. So we have the limit as x approaches 0 of e to the x minus 1 over x is equal to the limit as x approaches 0 of, in our numerator, we take the derivative of e to the x minus 1. In the denominator, we're once again just going to take the derivative of x. So we're just taking the derivative of the numerator, taking the derivative of the denominator. This becomes the limit as x goes to 0 of, up top, the derivative of e to the x minus 1 is simply e to the x. Down below, the derivative of x is again just 1. Evaluating this limit, we would have e to the 0th, otherwise known as 1. So the limit as x goes to 0 of e to the x minus 1 over x is just 0, or sorry, is equal to 1. So just a couple quick notes. Note, L'Hopital's rule applies in the case that our limit as x goes to c of f of x over g of x goes to 0 over 0 or infinity over infinity. So the cases we used were all 0 over 0, but infinity over infinity works as well. And c may equal plus or minus infinity as well. So we can use L'Hopital's rule whether we're doing limits at infinity or limits at a number in between. So for c equal to infinity, this will give us end behavior. So this is for doing end behavior. We'll take the limits at plus or minus infinity. Again, we only apply this when we have that 0 over 0 or infinity over infinity case. In future videos, we will see how we can manipulate other indeterminate forms into this type of indeterminate form. But this is the basics of L'Hopital's rule.